And thanks to all of you for being here. So I will talk today about quantum sensor networks, and please, interrupt me. It'll be more fun if there are questions. So quantum sensors are sensors that use quantum mechanics for sensing in a fundamental way. And because quantum sensors can be small, they can give rise to high spatial resolution. And because all measurements are fundamentally limited by the laws of quantum mechanics, quantum sensors can also give rise to high precision. So here are some examples of quantum sensors. One is this nitrogen vacancy center in diamond, which is a defect where you replace two carbons with a nitrogen and a vacancy. And this defect happens to have two levels, well, really more, but two levels whose splitting is sensitive to magnetic fields and temperature. And as a result, you can use the center as a magnetometer or a thermometer. And indeed, this has been used for magnetic imaging of live bacteria and nanoscale thermometry of live human cells. So another example that I really like are Rydberg atoms, which are atoms that have a highly excited outer electron. And you see that there is now a large distance between the positively charged core and the negatively charged outer electron. And this large electric dipole moment makes these Rydberg atoms very sensitive to electric fields. So these atoms can be very good electrometers. So here's just to emphasize how awesome quantum sensors can be. This is an experiment from Junyi at NIST Boulder. And what they were able to do is the following. So because of Einstein's theory of general relativity, two clocks at different gravitational potential click at slightly different rates. And what they did is in this experiment, so these atoms here are clocks. And what they were able to do is they were able to measure that atoms separated in vertically by less than a millimeter, they actually tick at slightly different rates. In other words, they measured this gravitational redshift across a millimeter, which corresponded to an astounding of a 10 to the minus 20th fractional frequency measurement, which is very impressive. So let me start really, really basic and show how the simplest quantum sensor works. So suppose you have a two-level system described by the Hamiltonian 1/2 theta z, where theta is a parameter of interest, and z is the Pauli Z matrix. So then you immediately see that theta is just the splitting between these two levels, and we want to measure it. So the way you do this, you prepare the state 0 plus 1, and then you evolve it under this Hamiltonian, and then the state 1 picks up a phase theta t relative to state 0. And then to measure this phase, you measure x, which is the Pauli X matrix, and then you get the two eigenstates of x with the corresponding probabilities. So you get p plus with a probability given by the overlap of plus with the state. That's just cosine squared theta t over 2. And you get minus with a probability 1 minus that. So at this point, now if you were to repeat this experiment many, many times, every time it will be a sample from a classical random variable whose probabilities, whose outputs are plus and minus, and probabilities are p plus and p minus, and they depend on this parameter theta. So this is this random variable, and these are these probabilities. So then we're trying to extract the value of theta by sampling from this classical random variable. So then an important quantity that quantifies how much information about about this parameter theta we have in the random variable whose distribution depends on theta, it's called the Fisher information. So it quantifies how much information about theta is in this random variable. And it's defined as follows. So you sum over the two possible outputs, plus and minus, and then you plug here either p plus or p minus, and then the important part here is this derivative. So you take a derivative with respect to theta. So in particular, the faster the probabilities vary with theta, the larger this derivative is, and the larger is the Fisher information. So this is roughly the intuition. But the reason why this particular formula is important is because of this Cramér-Rao bound. So the uncertainty delta theta in our estimate of theta, in the measurement of theta, after a single shot is lower bounded by 1 over the square root of the Fisher information. Now, in reality, you need to run this experiment many times, say m times, and then the Fisher information will be m times larger, and then in the asymptotic limit of large m, you can saturate this bound. But I'm going to, for simplicity, deal with this single shot formula. So let's now plug in our probabilities, P plus and P minus. And what you find is that the Fisher information is just T squared, so it's time squared. And so if you plug this in here, it means that the uncertainty in the measurement of theta is lower bounded by 1 over time. And perhaps this makes sense. You see that theta always comes as a product theta times t, and it kind of makes sense that for t that's twice as large, we should be sensitive to changes in theta that are half as small. So then for the rest of the talk, I will assume that for this simple problem, the uncertainty in the measurement of theta is just 1 over t. Okay, so now let's suppose we have n sensors. So let's suppose all n of these sensors are coupled to the same parameter theta. So then there are two approaches, at least for measuring this theta. One is just to use our sensors independently. So prepare each of them in this theta 0 plus 1. So I drop the 1 over root 2 in each sensor. And then each sensor gives me 1 over t uncertainty. And then because of this standard statistical reduction, I get 1 over square root of n improvement from n sensors. And this is called the standard quantum limit. That's the best you can do without using entanglement. On the other hand, if you're allowed to use entangled states, then actually you could start with this GHZ state, which is all zeros plus all ones. You can also call it a cat state. And then these two states are actually the lowest energy and the highest energy eigenstates of this Hamiltonian. They're separated by n theta. After time t, the state 1, 1 picks up a phase n theta t relative to the state 0, 0. And then in exactly the same way as in our single qubit example, from this phase, you can measure theta with an uncertainty 1 over nt, which is the thing that's multiplying theta in the phase. So you see here we have a reduction from root n to n in the denominator, because you can say that in some sense contributions to quantum noise from each sensor conspire to partially cancel each other out. And this is called the Heisenberg limit, and for this problem, it's the best possible measurement that we can do. So this reduction from 1 over root n to 1 over n, you can call it an entanglement advantage. So without entanglement, you have 1 over root n, and with entanglement, you get reduced to 1 over n. So now let's talk about quantum sensor networks. So suppose now instead of coupling our sensors to the same parameter, we couple them to different parameters theta I. So each sensor is coupled to its own parameter. But then instead of measuring every single parameter, I want to measure only one linear combination of them. And this linear combination I will call sum over I, alpha I, theta I. So here's a cartoon of how this could work. Imagine I have 4 sensors, and at each sensor, I have a field theta that is unknown. You can think of it as an electric field, a magnetic field, a temperature. And I also have a weight, alpha I, which is something that I pick. I want to measure this desired linear combination. So for simplicity, I will assume that these weights are real, but it's easy to generalize to complex weights. So why would I be interested in doing something like this? Well, you can think of this as making an aggregate query about our spatially varying field theta, or learning some collective property of that field. So if we have enough sensors, we can target some desired spatial profile of the signal, such as, for example, a Fourier mode or a spherical harmonic. So for this particular problem, we found the optimal protocol, and to explain it, let me assume without loss of generality that the alphas are not only real, I will assume that they're non-negative. So to make negative alphas positive, it turns out I can just apply a pi pulse which changes z to minus z. This flips the sign in front of theta, which is equivalent to flipping the sign in front of alpha. So let's assume they're positive. It's easy. And I will also assume that the largest alpha is equal to 1. So the reason why this doesn't lose generality is I can just take the largest alpha and divide this figure of this sort of quantity q by the amplitude of the largest alpha. So it's equivalent. So this is without loss of generality. Okay, and I will again start with the GHG state, all 0 plus all 1s, and then I'm going to apply clever pulses on my system to encode these weights alpha. And in particular, I would want the qubit I, in some sense, I want it to evolve for time that's proportional to alpha I, and then I will pick up that phase. So what do I mean by this evolve qubit I for time proportional to alpha I? So let's suppose I have 3 qubits. And then in here, I will write, so this is time. This is qubit 1, qubit 2, and qubit 3. And here, I will write the value of the Hamiltonian times 2. So for the first fraction of time, alpha 1t, I will just evolve under the full Hamiltonian. Theta 1 z1 plus theta 2 z2 plus theta 3 z3. And then I want to make sure that for this second fraction of time from alpha 1t to alpha 2t, only the second and the third qubit are coupled to their parameters theta, but the first qubit is decoupled. So how can I decouple the first qubit? Well, one possibility is right at this point, I can move this qubit to some other set of states that's not sensitive to the field, or maybe halfway through this red region, I can apply a pi pulse such that I pick up the phase of theta 1 going forward, and then I pick up negative theta 1 for the second half. And finally, for this last time fraction, I want only the third qubit to be coupled to its parameter. And again, to do this, I can either decouple the second qubit right here by hiding it in some other state or apply a pi pulse. Okay, so now that I've done this, you see that the first qubit is coupled to its parameter theta 1 for time proportional to alpha 1. The second qubit is coupled to its parameter theta 2 for a time proportional to alpha 2. And the third qubit is coupled for the entire time, which is proportional to alpha 3, which is 1. So the result is that after this entire time evolution, the state 1, 1 picks up a phase that's exactly proportional to Q because I designed it this way. So this is Q. And then if I measure now parity, which is the product of all the x's, then I find that the uncertainty in the measurement of Q is just the thing that's multiplying Q in the exponent here in the denominator in the uncertainty. So delta Q is 1 over T. And if I want it to be more general, if I release this assumption of the largest alpha being 1, it's actually given by the largest alpha divided by T. What we proved in this paper is that so not only this is achievable with this protocol, but it's actually the best thing you could do. Any questions on this?
Can't improve on the max.
You can't improve. That's asymptotically, that's really the best you can do. Yep.
The assumption is that all the three sensors are exactly identical?
Identical. Well, they're coupled, in this case, so they're qubits. And they're coupled, to these fields. I mean, they don't have to be identical. I mean, they can be, they can be very, very different. I mean, these fields can be like theta 1 could be a magnetic field, theta 2 could be an electric field. I mean, as long as I can write the Hamiltonian in this form, I'm in business. So there's no assumption of them being identical. I mean, they're identical as far as the math goes. I'm not sure if I'm answering the question.
Wait, in diamond, can you take exactly identical vacancies?
Identical what?
Identical vacancies?
They don't have to be identical at all, right? So, as I said, they don't even have to be like nitrogen vacancy centers. Like one of these can be a, nitrogen vacancy center coupled to a magnetic field, and another one can be, 2 levels, in a Rydberg atom coupled to an electric field. And as long as I entangled, these two qubits in the state 0, 0 plus 1, 1, and as long as I did this protocol, I would get it. So they don't have to be identical at all.
It's the fact that you could sum them up, with some dimensionless coefficients. I mean, it kind of means that there's the same physical quantity.
No, not at all. Like theta, we can have an electric field, let's say a magnetic field that's multiplying, some G factor. So that's times Z. So this will be, I'll be measuring the magnetic field times the G factor. So either I'll be measuring that quantity or I'll have to know what the G factor is to extract the magnetic field. And similarly, for the electric field that's coupling to my 2 Rydberg levels, I will need to know the sensitivity, of these 2 levels to the electric field. And then this electric field will be multiplying the sensitivity and again times the qubit. So, if you don't know anything about the sensitivity or the G factor, you'll be measuring a linear combination of some funny quantities. But if you know what they are, then you can sort of extract the linear combination of the corresponding electric field and magnetic field. Great questions, yes?
So it seems like, you are doing some multi-parameter sensing where the combination coefficients on the parameter will basically these alpha I, and then you have this matching lower bound. And I was wondering, to prove this matching lower bound, do you use quantum Fisher information matrix?
Yes. Yes, yeah, right. So, we have multiple parameters. So we do indeed use the quantum Fisher information matrix. On the other hand, we're interested only in one linear combination. So it's like a very unusual interplay between is it a multi-parameter problem? Is it a single parameter problem? But yes, we use the quantum Fisher information matrix. I didn't explain it, and I'm not going to explain it because I want to get to some newer stuff. I mean, this is old. I wanted to introduce it and move on to funner things. Great question. More questions?
So I'm just wondering, like, because I think like in the other bound in your previous slide, there was like the n factor, but this one's independent on the number of qubits. Is there like a
Oh yeah, right, right. Great question. Right. So let's consider a special case where we're interested in the average of these guys. So suppose each alpha here is 1 over n. So then you plug it in here, and you get actually 1 over nt. So you get exactly the Heisenberg limit that I introduced in the previous slide. Or another example, suppose I'm interested only in one of them. So suppose alpha 1 is equal to 1, and all the other alphas are 0. So then you plug it in here, you get 1 over t, which is just a single qubit example on my first slide. So it's all consistent. It's kind of actually interpolates between these two examples, which I had a separate slide on this, but I skipped it, but you made me talk about it. It's good. Okay, so another extension that we did after this is suppose instead of measuring a linear combination, so far we measured this linear combination, suppose you want to generalize and measure any desired analytic function, q of theta 1 through theta n. So then the optimum protocol in this case is very simple. You first measure individual theta I without using entanglement for some negligible fraction of the total time. And then you get estimates theta tilde I, and then you Taylor expand this function to a linear order around these estimates. So there's the q at the estimates, and then plus the first order Taylor expansion. And then you can use the optimal linear combination protocol to measure this linear coefficient. And then if you chose this negligible fraction of time sufficiently cleverly, then the higher order contributions will be asymptotically negligible. This turns out to be the optimal protocol. Okay, so we did lots of other extensions. It turns out if the coefficients alpha I are not uniform, suppose they're concentrated around a couple values, then to get the optimal answer, you don't really need to entangle all of your qubits. So you can use less entanglement to get the optimum answer. You can also generalize to the case where these theta I are correlated. So here's what I mean by this. Suppose you have this volcano here, 5 sensors around it that measure fields at theta 1, theta 2 through theta 5. So these fields can be a local gravitational potential or local gravitational acceleration. And then suppose they're not all independent. Suppose you really know everything about your volcano except for a few independent variables. For example, the density of magma in the magma chamber, or maybe, I don't know, also the height of magma in the magma chamber, but only like 1 or 2 independent variables. And so all 5 of these depend on these few independent variables. And then in this case, we also found the optimum protocol. But I don't want to waste time with this. This was still a while ago. I want to talk about some newer things. So here's the newer thing I want to talk about. So we're still, we just barely started writing it. In fact, we haven't even fully solved it. So suppose now you have the following scenario. So you have this quantum sensor network that I introduced earlier, and you have another term. So I assume that this Hint is a sum of arbitrary Pauli strings, except for these Z1 through Zn, with unknown coefficients. So this Hamiltonian is basically completely arbitrary, except that I know that the things that multiply Z1 through Zn are those theta 1 through theta n that I'm trying to measure. And here there's basically everything else. Everything else is allowed. And I still want some linear combination of these m thetas. So the motivation is I somehow want to measure this Q despite these unknown interactions. So I made my problem harder. Before I just had this, but now I have to deal with this unknown Hint. So we found the optimal protocol. So it goes like this. You first write your Hint as a sum of things that are diagonal on the computational basis, the things that are off diagonal. And then it's pretty obvious that you can eliminate all the off-diagonal terms using basically a form of dynamical decoupling, or in the modern language, Hamiltonian reshaping. What you just do is you just conjugate your qubits randomly with Zi's like this. So you break your full evolution under this Hamiltonian in little time slices. And then you conjugate each time slice, you take random qubits, and you conjugate each time slice with a Z. So here you conjugated the first qubit, you conjugated the third qubit and the fifth qubit, and the second qubit. And as a result, so what we get is something like this. So we get different evolutions uj with different probabilities pj. And I'm focusing here only on one time slice of duration delta t. And now, if this delta t is sufficiently small, I can Taylor expand to first order in h. Then I can take the sum, and then I can re-exponentiate. And what you find is that, if I ignore higher orders in delta t, that I just get evolution under an effective Hamiltonian that is just the average the Hamiltonian. So sum over jpj, uj dagger, huj. And it's immediately clear that, after I do this, all the off-diagonal terms go away. So as an example, let's suppose we had a single qubit. This is the most general Hamiltonian for a single qubit. And let's suppose with probability 1/2, I do nothing. With probability 1/2, I conjugate it with z. Then you immediately see that, these guys go away. Okay, so I've gotten rid of my off-diagonal terms, but I still have these diagonal terms. And again, I assume that they're arbitrary, except they have no support on these n simple generators. So let me now generalize the problem. Suppose I want to name all of these coefficients theta. So I goes from 1 to capital D, or D is 2 to the n. So I sum here over all 2 to the n diagonal generators. So GI are all possible products of Pauli Z matrices, and there are 2 to the n of them because each qubit either does or doesn't have the Z Pauli matrix. And now I want to measure some arbitrary linear combination Q of all 2 to the n of these coefficients. Okay. So first I'm going to assume that the coefficient theta1 in front of identity is 0. So I assume that G1 is identity, and the theta1 in front of identity is 0. Well, the reason I'm going to do this is because I will never be able to measure the coefficient in front of identity. I mean, it's just an overall shift. It's not measurable. So similarly, alpha1 that multiplies theta1, I'm also going to assume it's 0 because I cannot ask, for the coefficient in front of identity. So I'm going to assume it's 0. It's not measurable. Okay, so the first thing I'm going to do is, since I said that this Hamiltonian is diagonal, it's products of z's. So then we get some entries here on the diagonal, phi1 through phi d, that are somehow linear combination of these thetas. So to me, it wasn't obvious, but I think to most quantum information theories, it's obvious what linear combination of these thetas are these phi's. Kishore, do you know? You do.
So like phi1 should be sum of all the theta.
Which matrix do I use to change from the theta basis to this phi basis? Maybe it's not obvious. Okay, good. To me, it was not obvious at all. Okay, so the matrix is actually it's a Hadamard matrix to the nth power. So let me define this Hadamard matrix. So it's not the Hamiltonian. I'm sorry, it's the same letter. It's the Hadamard matrix without the 1 over root 2. And then this phi is actually the nth tensor product of Hadamard matrices acting on the thetas. So I mean, maybe it's clear, right? So like each of these G's is, if I say take the first row, I specify the value of the Z for first qubit, second qubit, third qubit, and each theta in each of these rows comes with either +1 or -1. And this Hadamard matrix just keeps track, is it coming with a +1 or a -1? I'll give an example later. Anyway, so phi is a linear combination of thetas, and it's a very simple linear combination given by the nth tensor product of this Hadamard matrix. So recall that Q is alpha dot theta. So it means that it's also some other vector b dot phi. So what is this matrix b? Well, I'm just changing a basis using this Hadamard matrix. So if I change theta to phi, I also need to change alpha to b. And actually, if I put in a 1 or a root 2 here, this thing would have been unitary. So, but I decided to put this entire 1 over d, 1 over 2 to the n in this formula for simplicity. But I'm just changing the basis. So alpha dot theta in one basis and b dot phi in the other basis. And the fact that alpha 1 is 0, it corresponds to the fact that sum over I bi is 0. Okay, let me summarize. I have this diagonal matrix with d entries. I want to measure some linear combination b dot, oh, that's a typo, it should be b dot phi. sorry, B of phi. And the sum over IBI is 0. So to explain now the optimal protocol for measuring this, let me first define capital B as being the sum over all positive BJs. So some of these B's are positive, some of them are negative. Let capital B the sum of the positive ones. It's also negative of the sum of the negative ones because the total sum is 0. And it's also the sum of the absolute values divided by 2. The sum of the absolute values is called the 1 norm. Okay, so now here's the protocol. I'm going to be coherently switching between the following states. So I'm always going to take 2 computational basis states. I will say what they are in a second. And I'll be picking up some phase, then I'll be shifting around what these states are, picking up some more phase, switching around and picking up some more phase. And eventually, I will accumulate a relative phase that's proportional to this Q. Again, this should be phi. I'm sorry. Okay, so what are these states here? So psi j will cycle through all computational basis states with positive bj. So again, remember, these are all computational basis states. I wrote this matrix on computational basis. So the different b's correspond to different rows here, different columns. So I pick all the computational basis states with positive bj and I cycle through them. And then this part of the superposition, I cycle through all computational basis states with negative bk. And then I decide how much time I spend in the given state psi j by the value of the corresponding bj. So the larger bj is, the more time I want to spend in psi j. And then in particular, if I spend the fraction, bj over b in state psi j, then I accumulate the phase, which is equal to time, times this 1/2 times the corresponding phase phi j, and then a minus sign because it's e to the minus iht. So this is the phase I pick up due to this state. And similarly, I want to spend time proportional to bk or minus bk in the state psi k prime. And as a result, I accumulate again the phase, which is given by the time, times the phase, times the minus sign, because I do e to the minus iht. So now we just put all of this together. And then the relative phase is just the sum over j over these guys minus the sum over k of these guys. And these are all the positive ones. These are all the negative ones. So I actually got all of them. So what I get is precisely the time t times the q I'm interested in. Again, this is phi, divided by 2b. So then the uncertainty, the measurement of q, is just 1 over whatever multiplies q in my phase. So it's 2b over t. And since 2b is just the 1 norm, I can write it as 1 norm divided by t. And this turns out to be the optimal. So prove that it's optimal. Now, how does this compare? Like, this is actually turns out to be entangled. I keep switching here between superpositions of basis states. And sometimes, they could be maximally entangled. One of these states could be the all 0 state, and the other one could be the all 1 state. So this will be like a GHZ state. So there could be a lot of entanglement. So is there an entanglement advantage? So the most naive product state protocol goes like this. You start with the state plus on all the qubits, then you evolve onto this Hamiltonian, and then you make some single qubit measurements, and you try to extract every single one of these phis. And then after you extract all of these phis, you just compute b dot phi. Again, this is a typo. And this doesn't work so well, because they're actually, they're exponentially many. There are d of these phis. So I really have to run a lot of experiments to measure every single one of them and compute. So this naive product state protocol, doesn't work so well. It has an extra factor of d to the 3/2 in here. And instead of the 1 norm, we have a 2 norm. So so 1 factor of d is explained by what I just said, because they need to measure every single one of these phis. That's how the naive product state protocol works. And there's another factor of d to the 1/2 that comes from the fact that if I choose b to be a superposition, maybe say the first entry of b is 1 and the second one is -1. So I want to measure phi 1 minus phi 2. But the generators corresponding to phi 1 and phi 2 are projectors on the computational basis states. They're very kind of multi-body observables. So it's also not surprising that for multi-body observables, entanglement really helps you a lot. So that's why there's another factor of d to the 1/2. Yes.
So it seems this naive protocol also gives you exponential information also, because you each of the phi 1, phi 2 up to phi d.
No, you can't get exponential information. I mean, every time you run the experiment, in either case, you can't get exponentially. You run the experiment once, then you measure all your qubits, you get only n bits of information. So you can't get exponential. Right?
Like in the previous case, you are directly getting b dot phi, but
Yes.
but here you are getting each of the phi. So b dot phi.
So here I'm not letting myself. So here I'm forcing myself at the end to make individual measurements, and I'm forcing myself to compute every single phi, measure every single phi, and then compute b dot phi.
Yeah. So that's my, so having just knowledge of b dot phi and having knowledge of each of the phi.
Oh yeah, I'm doing much more with this naive protocol. Yes, that's why it's so bad. Exactly, it's doing much more than that precisely. It turns out if you start with this naive product state, but you allow yourself to make collective measurements at the end, you can get rid of one factor of d. But then if I'm allowing myself to do collective measurements, I might as well prepare entangled states. So. Great questions. More questions? Okay, so let's do a 2-qubit example. So suppose this is my Hamiltonian. So identity times identity, identity z, zi, and zz, 4 parameters. I can also write it like this. So identity z2, z1, and z1, z2. And I'm going to assume that a theta 1 is 0 because I will not be able to measure it. And then I want to measure sum over alpha I, theta I. Where I'm going to assume that I just want to measure theta 2 plus theta 3 plus theta 4. It's just my choice. It's the example I want to do. And notice I assume that alpha 1 is 0 because I could not measure theta 1 anyway. So then, as before, this is a diagonal Hamiltonian. So the diagonal entries are phi 1, phi 2, phi 3, phi 4. So they correspond to these computational basis states. And if I did this Hadamard trick, it happens to be like this. So phi 1 happens to be theta 2 plus theta 3 plus theta 4, and you can compute all of this. You can easily check this. Very simple. Okay, so I'm interested in alpha dot theta, and if I want to write it in terms of phi, it's b dot phi, where b happens to be this. You can trust me. I mean, I did this calculation, so it's this particular thing. And now I'm looking at this vector b, and I know what my protocol is. My protocol says I first look at all the positive guys, and there's only one positive guy. So it means that one part of my linear combination is always going to be the state 0, 0, 0, 0, 0, excuse me. And then the negative coefficients, I have 3 of them, and they're all equal. So it means that the other half of my linear combination will be cycling through these 3 states. So as a protocol, I start with the state 0, 0 plus 0, 1, and I evolve for a third of my total time. So then for a third of my total time, so 0, 0 picks up a phase proportional to phi 1, and 0, 1 picks up a phase proportional to phi 2. So the reason for a 1/6, there's a 1/2 here, and there's 1/3 there. So now what I'm going to do is I'm going to swap these 2 qubits, like this. Because I want to switch from the state 0, 1 to 1, 0, and I do it coherently. And now I act for another time t over 3 by this Hamiltonian, so I get just another same factor same factor in front of phi 1, so it doubles. And then I get now a contribution from phi 3. So now I want to coherently switch to the state 1, 1. So the way I do it, I do controlled knot from the first qubit to the second qubit, so that this stays unchanged, but this 1, 0 changes into 1, 1. So I get this now. And then I finally evolve for the last fraction of time, t over 3. So this becomes a 3, and now I have also a phi 4 contribution. And of course, the way I designed it is that if I subtract now this phase from this phase, I get exactly something proportional to b dot phi. So the relative phase is exactly b dot phi times some coefficient, which I can write as a quantity of interest q times t divided by the 1 norm. So the uncertainty is exactly 1 norm divided by t, which is what I promised. So that's how it works. Okay, so so we found the optimal protocol for this problem. But now suppose we know that all but a specific poly n of these theta I are 0. So in fact, it's kind of crazy to assume that your Hamiltonian has all of these, z, 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 z multiplied, all the qubits. Like it's unnatural. So the natural Hamiltonians maybe will have 2-body interaction, maybe 3-body, probably not too much higher. So it's reasonable to assume that we know that almost all of the thetas are 0, and which we know which ones are 0, except for some polynomial number. Okay? So this means that if I know that some of the alphas are 0, I can set the corresponding thetas. If I know some of the thetas are 0, I can set the corresponding alphas here to arbitrary values because I know they multiply 0. So it means that I have, when I choose what B to use, I have some free degrees of freedom corresponding to these alphas that I can arbitrarily set. So in this case, the optimal protocol can indeed be found. You just need to find this one norm, but the smallest one over all allowed Bs, right? Because we have some degree of freedom here. So this problem happens to be called a basis pursuit problem, so it's a known problem. So some open questions that we're still answering is, so there are poly n of these thetas that are non-zero. The question is, will the optimal or approximately optimal solution be here? Will it be sparse? Will it in itself have only polynomially many non-zero entries? Because if B has exponentially many entries, it means I have to apply exponentially many pulses to the measurement, and it's kind of inefficient. And then the second question, if it is sparse, can we always find this optimal or approximately optimal solution efficiently? Yes.
So this problem seems very hard, right? Because this is on a sphere, right? I mean,
Right.
And then it's a non-convex set.
So B1, so the optimization of B1, well, yeah, I mean, so first of all, like if I just do it naively, right? I need to optimize B is exponentially large. So naively, I don't know how to do it efficiently. But maybe there's a clever method.
Yeah, like I'm saying that the non-convexity will hard because it's on a sphere.
Well, I mean, I think it's, the problem that is difficult is if I wanted to optimize B0. But B1, I mean, in principle, if I had polynomially many of these Bs, they'll be easy to optimize. And the problem is that I have exponentially many Bs to optimize over.
What is the issue? Maybe like, I might be wrong. Is that, let's say if you take two Bs and take their convex combination, that's not in the feasible set because then it's
maybe let's talk about this later, sure. Don't think about it while okay, so let me wrap this part up, and then I'll talk about one other thing quickly. So these quantum sensors can have applications at small intermediate scales or large scales. So at small scales, you can imagine the scale of a cell or human or molecule, and there you can measure magnetic fields, electric fields, or temperature with applications in chemistry, biology, and medicine. On the large scale, you can imagine an entire quantum network connecting sensors, or you can imagine doing measurements in geodesy and geophysics. You can imagine measuring magnetic fields, electric fields, temperature, and gravity. So as a summary of this part, and then I'll have another one short part at the end. So entanglement improves measurements of properties of spatially varying fields. So as an outlook, so far I talked about measuring a single property. You can measure multiple properties, but we don't yet know how to do this optimally. I consider commuting generators. We can also consider non-commuting generators, like, for example, if you have a vector magnetic field that's coupled to X, Y, and Z. There's quite some work on cases where there's some trust issues in your network. You want to do verified and or encrypted measurements. So in particular, we're writing a paper on including a so-called differential privacy quantum sensor networks. You can imagine that your parameters come from a discrete set, in which case it's sort of a discrimination problem rather than a human problem. There are lots of interesting questions about how to include errors and how to mitigate or error correct the errors. You can allow for the movement of sensors during the measurement. You can try to deal in the case where you don't have a limited amount of data, in which case this asymptotic bounds don't apply. Turns out the same ideas apply to oscillators, not just qubits, and there are lots of papers on this, including experiments. And finally, which is the thing I want to talk about for the last 10 minutes, is you can sense spatially correlated noise. Before I do this, any questions? Yes?
You go back to the previous slide.
Just one or no, before?
Or yeah. Which one of the applications do you think is most feasible for this?
So the most feasible, I'm not sure which one the most feasible. I'd say the most promising is probably the smallest one. So I think, first of all, the closer these defects or whatever, the closer the sensors are to each other, maybe the easiest they are to entangle. Maybe they're so close to each other that these electrons have a direct magnetic dipole-dipole interaction. So people have entangled, these centers using direct dipole-dipole interactions. And also, like, these quantum sensors are maybe most useful in cases where the things you're trying to measure vary like really quickly in space, and therefore you can use these tiny quantum sensors. So I think this is sort of the most compelling application. But I mean, if you've built a quantum network for other purposes, I mean, sure, you might as well entangle your quantum sensors across a large region. So I think these small kind of nano NMR type experiments are perhaps the most promising. Questions?
What's been done in terms of experiments?
Right. So, I mean, not much has been done on the qubit front. So I mentioned the same things hold for photons. And photons can either couple to like displacements of the photonic field, or they can couple to kind of through theta n. So theta can couple to the number operator, which is like the index of refraction. So there were some experiments on the photons with like microwaves. There may have been also an optics experiment. There was an experiment with cold atoms, but atoms were kind of treated collectively. So you can also think of them as oscillators, but not so much on the qubit front. These very simple experiments. Okay, so the remaining 10 minutes, let me talk about spatially correlated noise. So the question is, can one obtain entanglement advantage for sensing noise as opposed to field values? So the answer is yes. So it's these two recent papers. There's also some very nice work from Shimon Kolkowitz and Natalie DeLeon that kind of covers similar topics. Although so far they haven't really been talking so much about entanglement advantage, but they certainly talked about sensing spatially correlated noise. So let's talk about noise sensing. So suppose we have m qubits undergoing Gaussian Markovian dephasing. So what I mean by this, I have m qubits. Each qubit is subject to a fluctuating magnetic field, which I write like this. So each qubit has its own frequency, which I will drop later, and also a fluctuating magnetic field. I assume that each field is on average 0, but it's fluctuating, and the fluctuations are Gaussian and Markovian. So Markovian means that two time correlators are proportional to t minus t prime. And Gaussian means that it's sufficient to specify this 2-point correlator. So the entire dephasing process is determined by this matrix where the diagonal entries have strengths of local dephasing, while off-diagonal entries are correlations between these dephasings at different sites. Furthermore, I will assume, for the purposes of this talk, that there's only one unknown parameter. So I'll assume that this matrix is given by one known matrix plus the unknown parameter times another known matrix. And I just want to measure a single quantity because for simplicity, I want to do a single parameter problem. So for the experts, I mean, if you have the situation, you can rewrite the evolution of your qubits as being given by this Lindblad master equation, but I'm not actually going to use this formula. So you can just think of these fluctuating magnetic fields with these correlators. It's the same. So why would you want to do this kind of sensing the spatially correlated noise? So trapped ion qubits can be coupled to collective motion or to a common phase reference, and they would have the spatially correlated noise. You could have atomic array qubits driven by a global laser beam, and they would also give rise to this correlated noise. There are lots of applications to sensing spatially correlated noise in condensed matter. There's this very nice review here by Natalie and Eugene Demle and others. So, there's a lot of motivation for sensing noise, including spatially correlated noise. So the question is, does it help to entangle the initial state? Or maybe if I don't entangle the initial state, maybe I'll do just as well. So is there an entanglement advantage? So it turns out if the noise is uncorrelated, meaning that all of the off-diagonal entries are 0, and each qubit just dephases independently with its own dephasing rate psi gamma, then the answer is no. Well, if it turns out if the noise is spatially correlated, the answer is yes, and I will give 2 examples, and then I will close. So here's the first example. Suppose we have maximally correlated noise. So I'm going to assume that all of these fields are exactly equal. So they're fluctuating, but they're fluctuating exactly together. So this means that this matrix here is all ones. So every entry in this matrix is the same size. So it's fully correlated. And then without entanglement, you just get 1 over root n. So without entanglement, it doesn't really matter they're correlated. It's just the usual 1 over root n. However, with entanglement, you get a reduction, the usual kind of 1 over root n extra improvement. And the initial state is exactly our favorite GHZ state. And the intuition that is unlike in the case of uncorrelated noise where entanglement doesn't help, here the amplitudes of correlated noise processes add constructively and kind of give a boost. So maybe it's obvious. Anyway, so there's this improvement. So the second example is perhaps more interesting. Suppose there's very little noise in this one linear combination. So I sum up all the b's and I divide by root n to make it sort of sums this normalized. And I'm going to assume that this thing is barely fluctuating. So there's very little noise gamma psi or some psi much less than 1 in this linear combination. On the other hand, I will assume all orthogonal linear combinations have large noise gamma. So this one linear combination has low noise, everything else has high noise. So if you kind of work out through this example, you can compute what this matrix Cij is. So in particular, if psi is equal to 1, so if I wanted this thing to fluctuate just as much as all the other modes, psi 1 here gives delta JL, which is the same as uncorrelated noise. Because if I say that all modes fluctuate equally fluctuate either in this complicated basis or on the local basis. So it's the same as individual dephasing. And then if psi is much less than 1, well, you get this. So I mean, maybe it's not so intuitive that it should look like this, but it does. So this means that at psi equal to 0, this GHZ state, up to sort of coefficients, is actually the unique superposition that doesn't dephase at all. So I designed this my noise process in such a way that at psi equal to 0, this is the only thing that that doesn't dephase. I mean, there are like coefficients here don't matter. So on the other hand, at small psi, the state senses psi gamma, so it decays now with small psi gamma, but is hidden from this large noise gamma. And what this means is that so product states are either not sensitive to psi, if I just say basis state, I mean, it doesn't dephase at all, or if I take any other product state, say, I don't know, the all plus state, we'll have an exponentially small overlap with this GHZ state. And so what this means is that we actually have an exponential advantage for sensing psi, because there's just only one special entangled state that does really well, while all the product states do really, really poorly. So it's not that entanglement here works exponentially well, it's just that product states here work exponentially poorly because I designed my noise so cleverly. So maybe it's not so surprising. Okay, so to summarize, and I'm finishing now, so while there's no entanglement advantage for sensing spatially uncorrelated noise, we found an entanglement advantage for sensing spatially correlated noise. And we found a regime where this advantage is exponential. And this mechanism for this exponential advantage is sort of new for this entanglement advantage in sensing. It's not quite the same as the standard quantum limit versus Heisenberg. So we focused on qubits, but similar results hold for bosons and fermions, although we haven't solved it completely. So we have some results from multiple unknown parameters, but still many open questions. So, I said there is one unknown parameter, but we have some results from multiple ones. We have some results for sensing non-Markovian environments, but again, still many open questions. And we have very, very few results on evaluating the impact of unwanted decoherence, but still many open questions. So with this, let me thank lots of people who've contributed to this. And in fact, there's a recent collaboration with Lorcan, who is at A-star here, who's thinking about fault tolerance in quantum sensing. So let me thank the funding agency. So these are all the papers. These are some past and current group members, including Shore somewhere here. And thank you for your attention.